Okay. Stay for it.
Yeah.
In this program, we're going to take a look at sedimentary basins, their role in the formation of oil and gas.
In Unit 1, we'll consider basic terms, concepts, and basin-forming mechanisms.
In Unit 2, we'll develop a classification scheme for the different types of basins and take a look at the petroleum characteristics for each basin type.
And finally, in Unit 3, we'll compare the petroleum found in the major types of basins.
There are more than 600 sedimentary basins in the world, and about a quarter of them are producing petroleum today. Now, the fact that petroleum commonly occurs in sedimentary basins is the cornerstone of the sedimentary organic theory of the origin of petroleum.
Let's start with a few basic concepts. The sedimentary layers at the Earth's surface overlie a complex of igneous and metamorphic rocks that in continental areas we call basement. A sedimentary basin is a depression in the basement surface caused by subsidence. Geologists usually use the term basin to include both the depression itself and the thicker-than-average sediments that filled it.
Basins often change through time and can undergo several distinct stages. They can evolve from one basin type into another, as we'll see later. In some cases, an arch, which has thinner-than-average sediments over a basement uplift, can later founder and become a basin. An example of this is found in central Libya, where the Tibesti Arch persisted as a positive area for most of the Paleozoic and early Mesozoic. The northern part of this arch began to rift and subside during the Cretaceous, forming the oil-rich Sirte Basin. At this point, let's consider four major facets in the development of sedimentary basins: basin geometry, the nature of the sediment fill, tectonic style, and finally, basin-forming mechanisms. These four facets are mutually dependent and closely interrelated.
With regard to geometry, basins vary widely in both sizes and shapes. Some basins are circular or elliptical in map view. Others appear rectangular and trough-like. A basin can be symmetrical or asymmetrical in profile, or it can have an irregular cross-sectional profile.
It's tempting to believe that a basin was deepest where its sediments are thickest, but this isn't necessarily true. An example of this is a basin that received land-derived sediments from a single source direction, as in a delta.
Initially, the area of maximum deposition of a sedimentary unit, its deposenter, will be adjacent to the basin margin, and sediments will thin seaward. In time, the deposenter migrates laterally away from the basin margin toward the topographic low, where water depth is the greatest. At any one time, the basin's deposenter, the point of maximum basement subsidence, and the topographic low will probably not coincide. Basins can also be characterized by the sediments that fill them. They can be dominated by continental, shallow marine, or deep marine sediments, depending on their elevation and the interplay between the rate of subsidence and the rate of sedimentation.
Most sedimentary basins show that subsidence and deposition took place at about the same time. If sedimentation keeps pace with subsidence, no unfilled void ever exists, and the basin will be filled with shallow water sediments. At the other extreme, initial subsidence can produce a deep void that is later filled. This can produce some secondary isostatic subsidence as a result of sediment load. Basins that develop far from terrigenous sources of sediment, or that are isolated from them by topographic barriers or sills, may contain abundant carbonates or evaporites, depending on the paleoclimate. They may also be starved basins, filled mainly with water and receiving very little sediment.
Now, another important aspect of sedimentary basins is the nature and timing of tectonic processes. The types of folds and faults that develop within a basin are partly due to deformation mechanisms and partly to its sediments. Deformation by compression commonly produces folds and thrust faults. Extension leads to normal and block faulting. However, the presence of salt domes and growth faults is largely dependent on the basin's sediment fill. When considering the generation, migration, and accumulation of petroleum, the timing of structural growth is very important. Petroleum accumulation is often favored by active structural deformation during sedimentation, which leads to rapid changes in sediment facies and thicknesses. Organic-rich shales can be deposited in deep, structurally low areas, while coarser-grained reservoir facies and traps can develop over structural highs. Unconformities and faults are often present to assist migration processes.
When sediments both accumulate and are folded at the same time, anticlines may change in shape and amplitude, and their crests may shift laterally with time as they grow. This can make it difficult to decide just where to drill to locate an oil pool. For example, problems of this kind have been encountered in petroleum exploration in the northwest desert of Egypt. Structural deformation that occurs at a late stage of basin sedimentation can also assist the generation of oil, since it is often accompanied by higher than average heat flow. This oil will then move into structural traps. However, if structures are formed only after petroleum generation and migration have ceased, they may well be barren. Extreme tectonics following basin development can produce adverse effects. If deformation elevates the reservoir rocks to the near surface, groundwater invasion or erosion can occur, and with it, the degradation or loss of oil and gas. In contrast, high heat flow and deep tectonic burial of reservoir rocks can cause metamorphism and overmaturation of hydrocarbons.
Now let's consider basin-forming mechanisms using the widely accepted theory of plate tectonics. The location of basins with respect to the Earth's plates is fundamental to the classification scheme we'll develop in Unit 2.
The Earth's outermost shell is a rigid layer called the lithosphere, which consists of crust and uppermost mantle. Topographic lows form on the Earth's surface, where the crust is thin and composed of dense basaltic rocks. Oceans occupy these topographic lows, and thus the dense crust is called ocean crust. On the other hand, continental crust is thick, composed of lighter granitic rocks, and is therefore higher than ocean crust. Sedimentary basins form either on the continental crust or on intermediate crust at the boundary between ocean and continental crust, and transitional between them. The rigid lithosphere overlies a less viscous layer called the asthenosphere. Convection in the asthenosphere causes the rigid lithosphere to break apart into plates that move slowly across the Earth's surface. The interiors of plates are relatively stable, but their edges are tectonically active.
Plates break apart or diverge at mid-ocean ridges as basalt upwells from the mantle to form new ocean crust, and the seafloor spreads laterally. The forces involved are mainly extensional. Let's see now how this process starts over continental crust. Upwelling convection currents produce a dome-like bulge in the crust. When forces become too great, this bulge rifts in a radial pattern, usually with 3 branches. As plate separation takes place, only 2 arms of the rift actually continue to spread to become an ocean basin. The 3rd arm stops opening and becomes a failed rift. A modern example of this is the Red Sea and Gulf of Aden, which are an incipient ocean basin occupying 2 rift branches, causing Africa to rift away from Arabia. The long East African Rift Valley is being left behind as a failed 3rd arm. As the seafloor continues to spread, new ocean crust is added only at the axial zone, where a mid-ocean ridge begins to form. The separated continents are now far apart, and basins develop along their passive margins. This is analogous to the Atlantic Ocean margins today.
Where plates come together or converge, the dominant forces are compressional. Here, at a subduction zone, the leading edge of one plate overrides another, and the overridden plate is dragged down into the mantle and consumed. Island arcs can be created by volcanism and mixing of continental and ocean crusts near a subduction zone, and small basins will form adjacent to it. Subduction involves mostly ocean crust, since continents are too buoyant to be drawn down into the mantle. A continent on a plate's leading edge can compress and form coastal mountain ranges like the Andes. As the ocean crust that separates two continents continues to be consumed, the continents converge and eventually collide. Small basins form adjacent to the mountain uplifts in both of these situations.
At some convergent plate boundaries, crust is not consumed. For example, along the west coast of the United States, two plates slide by one another by means of long transcurrent faults. Small basins can form adjacent to such fault complexes, such as these California basins adjacent to the San Andreas Fault. Now let's turn to the manual and review these fundamental concepts before moving on to basin classification. And don't forget to do the exercises at the end.
Over the years, many different basin classification schemes have been proposed, as our thinking has evolved from the geosynclinal concept to plate tectonics. But in the petroleum industry, we need a classification that emphasizes the role of the sedimentary basin as a container for oil and gas.
Now, more than a third of the world's basins can still be considered frontier basins when it comes to petroleum exploration. Now, if we can find ways to group basins that have common oil and gas characteristics, we can relate this data to look-alike basins, whose petroleum prospects are unknown.
In this unit, we're going to present a classification that combines the schemes of both Huff and Clemmy. It is similar to many such schemes that are widely used in the industry. We'll present two basin types that are related to stable continental plates, two types that develop through plate divergence, and four types that relate to plate convergence. We'll then look at the unique features found in downwarped basins into small oceans, some of which are spreading and some shrinking. And finally, we'll discuss tertiary age deltas, which are later overprints onto the other basin types.
Of course, all basins are different, and not all geologists agree when it comes to assigning a particular basin to a particular class.
First, let's consider the two types of basins that are located in the interiors of present plates on the stable continental crust, or craton.
The first cratonic basin type forms only in the central areas of continents, so they've often been called interior or intracratonic basins. Some geologists call them sag basins because they form as simple sags or depressions on the underlying basement, but have no adjacent highlands. In plan view, they are circular to elliptical basins that appear saucer-like in cross-section, that is, symmetrical, shallow, and somewhat flattened. The origin of interior basins is still poorly known. Many of them are known to have block-faulted basement rock and attenuated crust, so the processes involved are mainly extensional. Some geologists think these may be areas of aborted rifting, where dense material was injected into the lower crust, reducing crustal buoyancy.
Some of the largest sedimentary basins in the world belong to this class, and some examples are the Williston, Illinois, and Michigan basins of the central United States and the Paris Basin of France. The Williston Basin is typical. It has a diameter of about 400 kilometers and is filled with up to 4.5 kilometers of sediment. The Paleozoic rocks are mostly shallow marine carbonates with lesser amounts of sandstone and shale. In the later Paleozoic, the basin became restricted by barrier reefs and evaporites were deposited. There were only minor marine incursions following the Paleozoic, the largest occurring in the Cretaceous. Mesozoic and Cenozoic sediments were mainly continental red beds and alluvial sands.
The Williston Basin produces oil and gas from many relatively small fields. Production is related to basement uplifts and regional arches, gentle anticlines draped over basement features, up-dip stratigraphic facies changes, and to widespread pre- and post-Cretaceous unconformities. Most production comes from Carboniferous age carbonates, but at least 13 different carbonate and sandstone formations, ranging in age from Cambrian to Cretaceous, have yielded oil or gas.
The sediment sequence and petroleum characteristics found in the Williston Basin are typical of many interior basins. They have only a single cycle of basin filling, usually with shallow marine or continental deposits, or a mixture of both. Most are Paleozoic basins that, at the end of the Paleozoic, became either non-depositional or received mostly non-marine fill. Basement uplifts, or arches, create traps in either sandstone or carbonate reservoirs, while stratigraphic and combination traps occur along the basin margins. Since they're located far from plate boundaries, geothermal gradients are lower than average. Consequently, time must play a major role in petroleum maturation, since many interior basins have never been deeply buried. The main risks in determining if there will be production from interior basins are the presence of adequate traps and the development of sufficient shale to act as both source rock and cap rock.
Some interior basins are simply too continental and have too few structures to be producers. But those that do produce often show one of two patterns.
They can have many relatively small fields, like the Williston Basin, which together may add up to considerable production. Or they can have one very large field associated with a major basement arch and long-distance migration. This field can contain well over half of the basin's total reserves. For example, in the Illinois Basin, the only interior basin that is known to contain a truly giant field, much of the oil was concentrated into lenticular sandstone bodies, which developed over the central La Salle Arch. A second basin type that belongs to the stable craton develops more towards the margins of continents, so they're often called foreland or craton margin basins. They're also sometimes called composite basins because they evolve in two stages from the interior basin type.
In foreland basins, the first depositional cycle was interrupted by uplift, usually in the late Paleozoic or Mesozoic. Then a second cycle began, most commonly from a different direction. A regional unconformity separates these two depositional cycles. Although the basin was initiated by extension, the dominant processes in the second cycle are compressional, related to the uplift and orogeny. Foreland basins are usually elliptical or elongate, vary widely in size, and have asymmetric profiles. North American oil-producing foreland basins include the Alberta, Anadarko, Permian and Appalachian basins, and most of the small Rocky Mountain basins. The Oriente Basin of South America and the basins of Algeria also belong to this class.
As an example, let's look more closely at the Permian Basin of West Texas. The first cycle early Paleozoic sediments were mostly shallow marine carbonates. During the Upper Carboniferous, the Marathon uplift rose to the south and the basin was renewed and deepened. The second cycle began with thick clastic deposits derived from the uplift, but evolved into a reef-bound evaporite sequence during the Permian. Like many foreland basins, the Permian Basin is also composite in that it can be divided into two smaller basins, separated by a prominent arch.
In the Permian Basin, petroleum is found in both first and second cycle reservoirs. Production from first cycle early Paleozoic sediments is in structures related to basement topography. Second cycle late Paleozoic production is from anticlines below salt and from reef-related facies.
Like the other cratonic basins, foreland basins are often mixtures of both carbonate and clastic sediments, or they can be mostly clastic. However, in either case, petroleum reservoirs in foreland basins are mostly found in sandstones.
As we saw in the Permian Basin, production occurs in both the lower and upper depositional stages and is related to basement features in the first cycle and to anticlines and stratigraphic facies in the second.
Now, like all cratonic basins, foreland basins tend to be cool, but they have a greater range of geothermal gradients than interior basins, and their gradients may be above average.
Furthermore, since these basins are deeper, are less likely to be continental, and are more likely to be evaporitic, their petroleum potential is usually better than that of interior basins.
The field size pattern is the same, however, with either many small fields or one outstandingly large field that dominates the basin's reserves.
Now let's turn to a third basin type that forms on continental crust. However, this one can be closely linked with plate divergence and seafloor spreading, the rift basin. We saw earlier that these basins form as down-faulted failed arms, where continental plates are stretched but do not completely separate. They are usually fairly small, linear basins that can be either deep or shallow. Horst and Graben tectonics give them an irregular profile. Rift basins include the Sirte Basin of Libya, the Rhine Graben in Europe, the Gulf of Siam, the Suez Basin of Egypt, and the Viking Graben of the North Sea. Let's look more closely at the last two examples.
The Suez Basin of Egypt contained only thin Paleozoic and Cretaceous non-marine sands until it began to rift in the Cenozoic. During the Miocene, a 1 to 2 kilometer thick complex of sandstone and organic-rich shale developed, with facies closely controlled by fault block movements. Later, evaporites and clastics were deposited. Oil is found mostly in pre- and post-rift sandstones and in some pre-rift limestones on the upthrown sides of faults. Traps are sealed both above and laterally by the evaporites or the Miocene source shales.
The Viking Graben of the North Sea began to form as one arm of a radial rift in the late Permian, but the major faulting occurred during the late Jurassic. Two branches became the Atlantic Ocean and split off Greenland from the rest of Europe. The Viking Graben became a failed rift. It contains up to 4 kilometers of pre-rift sediment, mostly red beds, deltaic and marine sandstone, and shale of Mesozoic age. There are also several kilometers of post-rift fill, starting with organic-rich shale and followed by marine sandstone and chalk. In the Viking Graben, productive reservoirs occur mainly in the pre-rift Jurassic sandstones, in tilted fault blocks capped by Upper Jurassic organic-rich shale. These shales acted as both source rock and seal. Some post-rift sandstones and carbonates are also productive.
Now, most rift basins are filled mainly with clastic sediments, either marine or non-marine. But warm ocean or restricted rifts often contain abundant carbonates and evaporites. Now, depending on the facies developed, either limestones or sandstones can be petroleum reservoirs.
These are sourced by overlying or laterally interfingering shales with short migration distances. Combination traps, where shallow water facies and unconformities develop over differentially subsiding blocks, and anticlinal drape traps are most common. Basin restriction frequently produces evaporite seals, as in the Suez Basin. Geothermal gradients in rift basins are frequently higher than average. This isothermal contour map of the Gulf of Suez shows gradients that range from 2 to 4 degrees centigrade per 100 meters.
For these various reasons, rifts can be quite petroleum-rich basins, even though they're small in size. The critical risks for production are adequate development of an organic-rich source shale, sufficient trap size, and geothermal gradients that may be too high. Productive rifts can be either oil or gas prone, and their crude oil types vary widely.
As we saw earlier, not all divergent zones will become failed rifts. Some will evolve into pull-apart basins as the seafloor continues to spread and basaltic ocean crust is added. These basins form next to the trailing edges of continents that have been split apart, and for that reason they're sometimes known as passive margin basins.
Pull-apart basins are long, linear, asymmetric basins with a one-sided continental source. They occur mostly offshore on intermediate subbasin crust. Most of the world's pull-apart basins are located on both sides of the Atlantic and Indian Ocean margins. Productive basins of this class include the Gabon Basin and Angola Cabinda off the west coast of Africa, the Northwest Australian Basin, and Hibernia off southwest Newfoundland.
All pull-apart basins began as rift basins during the Permian or early Mesozoic. The Gabon Basin off the west coast of Africa illustrates this. The initial pre-Jurassic rift was filled mostly with non-marine clastics. The active separation stage began in the Cretaceous. As the rift began to evolve into a pull-apart basin, shallow marine sands, carbonate and evaporite, were deposited. As more open marine conditions developed, a thick prograding clastic fan was laid down. This sediment load produced salt diapirs in the underlying evaporites.
Source rocks and oil production are found at all sediment stages. Clastics from the initial rifting are productive in fault block-related traps. In the shallow marine sequence, oil occurs in anticlinal drapes over the higher blocks. Most production, however, occurs in the post-rift clastic wedge, in traps related to salt diapirs.
A few pull-apart basins have been well explored, so it's hard to generalize about their petroleum characteristics. They produce mainly from deep sandstones, related to either the rifting or spreading stages. Shale or evaporite cap rocks are equally common. The traps are usually moderate-sized combination or anticline traps, related to basement uplifts in the initial rifting stage and rollover anticlines in the passive margin stage. And salt diapirs are often important, as in the Gabon Basin.
The geothermal conditions of pull-apart basins are still not well known. Probably gradients were high in the initial rifting stage and low during the accumulation of the post-rift clastic wedge.
The critical risks to production are mainly sufficient burial and kerogen maturation, the development of source shales in the initial rift stage, and the development of reservoir sands in the post-separation stage. Now, let's look at 4 basin types that form when plates converge near continental margins.
These are the fore-arc, back-arc, non-arc, and collision basins. All 4 convergent margin types have a number of features in common. They are small, linear, trough-like basins that form over intermediate crust. They are Cretaceous and Tertiary in age, and are mainly filled with immature, clay-plugged sands and shale. These basins develop quickly and are as quickly destroyed by plate convergence. Their tectonic development is complex. The overall tectonic regime is compressional, but considerable strike-slip and block faulting occur. Most of the world's convergent margin basins are associated with the Pacific Ocean.
There are 2 types of basins that are found near subduction zones that have developed island arcs. Back arc basins form between an island arc and continent. They receive mostly shallow water sediments. Heat flow, measured from back arc basins, is high to very high.
Fore-arc basins lie between the island arc and the ocean trench. Their sediment facies are quite variable and can range from fluvial to deep-sea fan. In contrast to back arc basins, fore-arc basins have abnormally low heat flow because of the under-thrusting of the cool ocean plate.
Indonesia provides a good example. Several back arc basins have developed behind the island arc and adjacent to the stable continental Sunda shelf. Smaller fore-arc basins are found in front of the island arc. Both types run parallel to the trench arc system. Let's look more closely at a cross-section through the Sumatra back arc and Mentawai fore-arc basins.
The Sumatra Basin is filled with up to 5 kilometers of late tertiary clastic sediments, with only small amounts of limestone. However, because of the very high heat flow, even such young sediments are oil productive at depths of less than a kilometer. In contrast, the fore-arc Mentawai Basin, which is both shallower and has low heat flow, is not commercially productive. A major reason for this is the lower than normal thermal gradient, caused by the descent of the cool oceanic plate. Non-arc basins are formed along convergent margins where the plates move by transcurrent faulting. Consequently, they're sometimes called strike-slip basins or California-type basins because they're common along the west coast of the United States. Non-arc basins are small basins that form through a combination of both the transcurrent movements and normal block faulting. In addition to the California basins, non-arc basins include the Vienna Basin and the Crimea and Baku basins of the Soviet Union.
Here we see two examples from California, the Los Angeles and Ventura basins. These basins trend at a high angle to the San Andreas fault system, a pattern which is typical for many non-arc basins. A cross-section through the Los Angeles basin shows that it is filled mostly with thick, young clastic sediment. Oil production is from anticlines, and most of the oil is reservoired in thick Miocene to Pliocene, deep-water, clay-rich sands. For its small size and young age, the Los Angeles basin is very prolific. This may be attributed mostly to its high geothermal gradient.
The adjacent Ventura Basin has a similar but even thicker sediment fill. However, its geothermal gradient is only average to below average. As a result, its oil fields are both fewer and smaller than those of the Los Angeles Basin. Collision basins, sometimes called median or intermontane basins, are small basins formed within marginal fold belts, either where two continents or continental coastal mountains and a trench have collided. Some geologists consider this a type of back arc basin, but a well-defined trench arc system is usually no longer present. The tectonic and sedimentary conditions are similar, however. Collision basins form through a combination of local strike-slip and extension within an overall compressional setting. Their geothermal gradients are usually high, and the sediment fill is clastic.
Many of the world's collision basins are associated with either the Andean trend of South America or occur along the east-west Tethyan trend, where Africa is colliding with Europe and Asia. Examples include the Maracaibo Basin of Venezuela and the Pannonian Basin of Hungary. The four small convergent basin types, forearc, back arc, non-arc, and collision basins, share a number of petroleum features. They mainly produce from sandstone reservoirs at shallow depths and often have thick or multiple pays. Traps are moderate-sized, mostly block uplifted anticlines, and some combination traps. These basins are typically oil-prone with low gas enrichments.
Even though their sediments are quite young, the high geothermal gradients make prospects good in many back arc, non-arc, and collision basins. But forearc basins are often poor prospects, due mainly to their immaturity and low geothermal gradients. Deformation that is too intense, igneous activity, and the poor reservoir properties of immature clay-rich sandstones can be problems in any of these convergent basin types.
Now we'll consider the special case of sedimentary basins that are downwarps into small oceans. These are large to medium-sized linear, asymmetric basins that are found along the margins of present or past small oceans. Many classifications do not recognize downwarp basins as a separate category from the ones we've already discussed, but their sedimentation and petroleum characteristics do make them somewhat different.
Some downwarps are related to the opening of small ocean basins. The Gulf Coast and East Texas basins and Alaska's North Slope belong to this type. Other downwarp basins form in small, closing oceans. This type is often found along the Mediterranean and Tethyan trend and includes the most petroleum-rich basin in the world, the Arabian-Iranian Basin.
However, the sediments and structures are similar in all downward basins, regardless of whether the ocean is opening or closing.
Open downwarp basins can evolve in time into closed downwarps through the convergence of continental plates.
More advanced collision can cause these to turn into trough-like downwarps, such as those in Italy, North Africa, and the Palesti Basin of Romania. Let's look briefly at the Gulf Coast Basin of southern United States. The basin initiated through Upper Paleozoic rifting. Basal evaporites were followed by up to 12 kilometers of shallow marine clastics and carbonates. Rapid tertiary subsidence produced salt domes that are important in Gulf Coast production. Stratigraphic wedge-out traps at the basin's edge created large fields in sandstone reservoirs. Geothermal gradients are above average in the Gulf and increase inland.
The Arabian-Iranian Basin is a downwarp into a small closing ocean, and the Arabian Gulf is a remnant of the once extensive Tethyan Sea. Arabia is being overridden by the Asian continent along a plate boundary located northeast of the basin. These processes created ideal restricted basin conditions for petroleum formation and abundant anticlinal traps. Source rocks were formed during transgressions in a starved basin setting. Regressions produced reservoir sands and widespread evaporites at many horizons. Jurassic limestones and dolomites are the major reservoirs in the west in Saudi Arabia. Toward the basin center, production comes mostly from Cretaceous lenticular sandstones, and the overthrust eastern margin in Iran produces mostly from thick tertiary limestones and reefs. Downwarp basins in small oceans are among the richest petroleum basin types, as we've seen, and together they contain nearly half of the world's reserves.
The sediment facies often associated with small, restricted oceans, such as salt and organic-rich shales, are combined with above normal to high geothermal gradients, providing ideal conditions for oil and gas.
It's getting late. You want to get back to it?
Yeah, let's do that.
The sediment fill is mostly a mixture of shallow marine carbonates and clastics, and reservoirs occur about equally in either sandstones or porous limestone. Petroleum usually has its source in laterally interfingering and overlying shale, but marls and limestone are important source rocks in some basins. Traps are mostly anticlines, either drapes over basement highs or compression folds, often assisted by salt flow. Stratigraphic traps, both lithologic pinch-outs and reefs, and combination traps, are particularly common in downwarp basins into smaller opening oceans, like the Gulf of Mexico. The traps of downwarp basins are commonly sealed by either shale or evaporite.
These basins contain mostly intermediate or mixed gravity crudes, but petroleum chemistry can vary widely. Oil is mostly produced from intermediate depths, but at deeper levels, thermally altered gas can be significant.
The tertiary deltas are the last basin type in our classification. And in a sense, they're not true basins, but later overprints onto other basin types. They can form in any coastal setting and are found about equally over convergent and divergent margins. Deltas are small to medium-sized, thick accumulations made up entirely of land-derived clastics. Rapid deposition, seaward progradation, and differential compaction produce growth faults, rollover anticlines, and flow structures. Geothermal gradients are typically low, due in part to the sediment thickness and overpressuring. The Niger Delta of West Africa is a good example. It formed over a pull-apart basin topped with Cretaceous deep-water shale. The three formations that comprise the delta cut across timelines, but are thickest in the Miocene. Pro-delta shales, which are the source rocks, are overlain by delta front interbedded sandstone and shale. Delta plain sands are fairly thin. Production is mostly from rollover anticlines developed down-thrown to growth faults in multiple pay pro-delta sands. There are over 140 fields, but the largest ones lie close to the delta's depocenter, where the structures are less complex and the overpressured zone is deepest.
The Mississippi Delta is similar to the Niger in its age, sediments, structures, and petroleum production.
But it has the further advantage of an underlying Mesozoic salt, which produced diapir structures.
Together, the Niger and the Mississippi Delta contribute 90% of the world's known reserves from deltas.
Deltas are mostly filled with upper tertiary clastics and have low geothermal gradients, so their petroleum reserves are often fairly deep. Reservoirs are entirely in sandstones, source rocks entirely shale. Traps are usually formed by small to moderate-sized gravity features, such as growth faults, rollover anticlines, or mud and salt flow structures.
As a result, deltas may contain a multitude of small fields and on the whole make fairly rich petroleum basins, but they largely lack giant field production.
The critical risks in delta exploration are mainly the small size of traps and the absence of a good cap rock. Now, most of the kerogen in the source rocks is land-derived and vitrinite-rich, so deltas are often gas-prone.
Now let's turn to the manual and review these 10 basin types and their petroleum characteristics. And don't forget to do the exercises.
In this unit, we're going to compare the petroleum characteristics of sedimentary basins using the classification scheme we've just developed. Let's look first at the 25 sedimentary basins in the world that are the richest in terms of known petroleum reserves. Together, these basins contain nearly 90% of the world's oil and gas. A breakdown of these petroleum-rich basins by basin type shows that 8 of them belong to the downwarp basin class, and an additional 7 are large foreland basins. Of the remaining 10, 3 of the basins are rifts and 2 are deltas. Finally, there are 5 convergent margin basins, including 3 non-arc, 1 back arc, and 1 collision basin type. 3 basin types are not found on this map of the world's richest petroleum basins: the interior, the pull-apart, and the four-arc basins. Here is a histogram which shows the distribution of the world's known petroleum reserves according to the basin types. This graph is based on data published by Clemmy in 1980. Again, we see that downwarp basins and foreland basins dominate the world reserves, but considerable reserves are found also in rifts, deltas, and convergent margin basins.
One of the critical factors to oil generation and production is the amount of sediment that is found within the depth range of the oil and gas windows. We can divide the total world sediment volume that lies within this range according to basin type. Note the striking similarity between this graph and the one we'd just seen. For the most part, the proportions are the same within a few percentage points. However, there are 2 notable exceptions: the downwarp basins, which are exceedingly rich for their sediment volume, and the pull-apart basins, which appear petroleum poor.
On the average, downwarp basins have yielded much more petroleum per unit sediment volume than any other basin type. High petroleum-yielding basins in any class can usually be related to special features that enhance their source, reservoir, cap rock, and trap potential. And these special features are most often optimal in downwarp basins. The most striking example of this is the Arabian-Iranian Basin, which is the world's richest petroleum basin. In contrast, known reserves from pull-apart basins seem low when compared to the sediment volume that lies within the oil and gas windows.
However, 90% of these basins lie in offshore areas, more than half in deep water, and they've received relatively little exploration effort. Pull-apart continental margins may truly be one of the last frontiers for petroleum exploration.
A basin's geothermal regime will influence the depth of petroleum formation and migration, and is a major factor in determining the depth of production.
This graph plots for each basin type the percentages of worldwide reserves that have been found at each of 3 depth levels. Shallow production, at depths of less than 2 kilometers, predominates in the 2 cratonic basin types. Even though these basins are geothermally cool, old Paleozoic rocks dominate, and time, therefore, has played a major role in maturation. Furthermore, uplift and erosional stripping has raised these old source rocks and reservoirs to shallower depths. Shallow production also is dominant in the hot convergent margin basins, where a high to very high thermal gradient can produce maturation in even young shallow source rocks. Mesozoic and Cenozoic basins with higher than average gradients, like the rift and downwarp basins, mostly produce at moderate depths of from 2 to 3 kilometers. Cool, young pull-apart basins and deltas usually produce from greater depths, between 3 and 5 kilometers, where temperatures become high enough to cause maturation.
Often a basin's petroleum richness depends on the presence or absence of giant fields. Giant fields are those that contain over 500 million barrels of recoverable oil, or greater than 3.5 trillion cubic feet of natural gas.
Now, although such giant fields make up only about 1% of the world's petroleum fields, they contain about 75% of all the oil and gas that's ever been found.
This histogram is based on the historical record of finding giant fields. As you can see, there is a high chance of finding giant petroleum fields in foreland, rift, non-arc, and closing and opening downwarp basins. Deltas generally contain very few giant fields, and they are almost unknown from interior and fore-arc basin types.
Let's now look at how the petroleum fields within a basin are distributed by size, ranking them from largest to smallest. In some basins, the largest field can contain 50% or more of the total reserves. As we've mentioned earlier, this pattern is found in many cratonic basins that have extensive regional arches. For example, the Hassi Messaoud field, which we discussed in Module 4, contains nearly 2/3 of the total reserves of the foreland Triassic basin of eastern Algeria. This pattern is also found in some collision basins, such as the Maracaibo Basin of Venezuela, where the largest field contains 3/4 of that basin's petroleum.
Here we see a more typical field size spread, where the largest field contains about 30% of a basin's reserves. This pattern is found in many basin types, including most rifts, downwarp basins into opening oceans, back arc, non-arc, and the remainder of the collision basin types.
Cratonic basins usually have this pattern. Provided there is no extensive arch to concentrate the petroleum into one area, and there are many small fields, the largest contain only about 1/10 of the basin's oil. The Foreland Appalachian Basin of the eastern United States is an example of this type. Downwarp basins into small closing oceans also tend to have this pattern. Finally, deltas contain a profusion of relatively small fields, with the largest containing only 3 to 4% of the basin's reserves.
The types of crude oil found within a basin and the oil-to-gas ratios are more closely related to the kerogen type, sediment fill, and the effectiveness of the caprock rather than to the basin's architecture.
However, a few generalizations can be made. Land-derived clastics deposited near continental drainage areas yield low-sulfur paraffinic to paraffinic naphthenic crudes. These would be found mainly in basins formed over intermediate crust, such as the pull-apart basins, deltas, and the convergent margin types. Marine carbonates, or clastics deposited in restricted silled basins, contain marine-sourced kerogens and tend to yield high-sulfur aromatic intermediate to asphaltic crude. This would typically occur in basins formed over continental crust, such as rifts, and some cratonic basins. Mixed sedimentary facies and kerogen types, such as those found in downwarp basins, result in mixed crudes. In almost any basin, however, crude oil tends to become lighter, both with depth and with age. For example, the old Paleozoic source rocks that are common to cratonic basins tend to yield high-gravity, low-sulfur crude. Natural gas is particularly associated with two basinal settings. First, it is abundant downwarp and in large old foreland basins where there is deep thermally altered methane. And second, it occurs in young, high-volume basins that have an abundance of land-derived type 3 kerogen, for example, deltas. A good caprock is, of course, essential to the development of large gas fields, since natural gas can so easily be lost.
Ready to go?
Yeah.
Giant gas fields require either extensive evaporite caprocks, such as those commonly developed in foreland and downwarp basins, or regional hydrate barriers developed in cold Arctic permafrost areas. The shale cap rocks found in the smaller and hotter basins, that is, rifts, back-arc and non-arc basins, appear to have been prone to gas leakage.
These basins yield mostly oil. Interior cratonic basins also have low natural gas enrichments because they're shallow and cool and their reservoirs had been subjected to frequent erosion.
It's important to remember, however, that these are only generalizations, and every sedimentary basin is different. In any class, there will be some basins that are prolific, some that are productive, and some that are essentially dry.
What matters most is that special combination of sediment fill, age, depth, temperature, structure, and timing that makes each basin unique and makes petroleum exploration a great challenge. Do you know the way up?
Well, no, do you have the map?
No, I gave you the map back up on the head wall.
You didn't give me the map.
I put it right... Oh, no. It's still... Come on, it's getting dark. I think we went that way. No, we went back this way.
This program has been sponsored in part by the following companies: Agip, Aramco, City Service, Dome Petroleum Limited, Gulf Oil Corporation, Mobil Oil Corporation, Phillips Petroleum Company, Standard Oil of California, Texaco Incorporated, IHRDC and these companies, by their sponsorship, do not in any way guarantee or represent the accuracy of the content or methods contained herein. The user hereby agrees to hold IHRDC and the sponsors jointly and severally harmless from any and all damages, including legal expenses, which may arise from the use of this program. No portion of this videotape may be reproduced without the permission of IHRDC.